So this will be the third lecture out of chapter 11, so this should be the last lecture. So we'll just continue looking at the reactions of alcohols. In this particular lecture, we'll look at how alcohols can be oxidized. So they can be oxidized to aldehydes, ketones, carboxylic acids. So again, we'll just summarize the different reactions in this chapter here. So if you have a primary alcohol, then they can be oxidized to an aldehyde. And so a variety of different oxidizing agents that we'll talk about. So these are the more weak or mild oxidizing agents like PCC, PDC, a Swarin oxidation, or a reagent called DMP. So what's important to note is that primary alcohols can also be oxidized to carboxylic acids. So that depends on what oxidizing agents you use. If you use one of these oxidizing agents, it'll stop at the aldehyde. If you use one of these oxidizing agents, which are much stronger oxidizing agents, they will oxidize the primary alcohol all the way to the carboxylic acid. And if you have a secondary alcohol, then they can be oxidized to ketones. So any of the oxidizing agents that we talk about in this chapter will oxidize a secondary alcohol to a ketone. And then we'll look at oxidation of diols as well, 1,2-diols or vicinal diols. So if the OHs are on adjacent carbons, then you can oxidize them with periodic acid. Okay, so before we get into those reactions, so let's just talk a little bit about oxidation and reduction. So from General Chemistry 1 and 2, we talked about oxidation and reduction reactions a lot. So in general chemistry definition, right, oxidation is defined as the loss of electrons, and reduction is defined as the gain of electrons. So if you remember the acronym OREG. So organic chemists tend to think about oxidation and reduction a little bit differently. The same definitions apply. It's still gain and losing electrons, but organic chemists will tend to think of oxidation instead as a loss of CH bonds or a gain of CO bonds. And then the reduction, the opposite. The addition of CH bonds in a molecule would be reduction, and the loss of CO bonds would be a reduction. Or in even more general terms than that, if you define it in terms of the gain, oxidation is the gain in the number of bonds from carbon to an atom that is more electronegative than carbon, and that would be an oxidation. And the opposite would be a reduction. If we reduce the number of bonds from carbon to something more electronegative than carbon, then that's going to be a reduction. So some examples. So this is a reaction from organic 1. If you take CH4 and do a free radical chlorination. So if you remember what happens in this reaction, you lose a hydrogen from the molecule and you pick up a chlorine. So you increase the number of bonds from carbon to something more electronegative than carbon, since chlorine is more electronegative than carbon. So the carbon has been oxidized. So this is an oxidation reaction. Or if you had an alcohol, so in this case you have one bond to oxygen, and if you converted that to a ketone, now you have two bonds to oxygen. So you increase the number of bonds from C to O, that's an oxidation. So oxidation is oftentimes abbreviated with the symbol of oxygen in brackets. And so again, you've increased the number of bonds to oxygen, or in more general terms, you increase the number of bonds from carbon to something more electronegative than carbon, since oxygen is more electronegative than carbon. So examples of reduction, if we took this alkene, so we looked at this in chapter 8, hydrogenation adds hydrogen and hydrogen across the C double bond C. So that's a reduction, right? You increase the number of bonds from carbon to hydrogen. So how about this reaction? So we looked at how alkenes react with HBr, if you remember that reaction. So take the pi electrons, make a bond to carbon, which makes this carbocation, and then Br minus adds to that carbon. So this would be your final product. So you added H and Br across the C double bond C. So would that be oxidation or reduction? Well, this would be neither. And one way to think about that is, so you increase the number of bonds from carbon to hydrogen, that would be reduction. But you also increase the number of bonds from carbon to something more electronegative than carbon, so that would be reduction. So overall, it's neither oxidation or reduction. Okay, so if you're given this example, so if you took this ketone and made this ester, would that be oxidation or reduction? And so you increase the number of bonds. So this has 2 bonds to oxygen, and this has 3 bonds to oxygen, so that would be an oxidation. So in general, if you have carbon-based compounds, so it doesn't have to be again to oxygen. You could be making bonds to fluorine or nitrogen or chlorine. They're all more electronegative than carbon, and that would be oxidation. But so if you started with CH4 and made methanol, so now you have 1 bond to oxygen, that would be an oxidation. If you went from the alcohol to the aldehyde, now you have 2 bonds to oxygen, so that would be an oxidation. Or to the carboxylic acid, now you have 3 bonds to oxygen, that would be an oxidation. And to CO2, that would be carbon in its most oxidized state, so that would be another oxidation. And of course, if you go backwards, so CO2 to carboxylic acid would be a reduction, or carboxylic acid to a ketone would be a reduction. Aldehyde to an alcohol would be a reduction. And we looked at examples of how to do that back in chapter 10, right? If you wanted to go from here to there, you could do something like H2 and palladium, add hydrogen and hydrogen across the CO bond, so that would be a reduction. Or methanol down to CH4, decrease the number of bonds to oxygen, that would be a reduction. Okay, so let's look at some specific examples from this chapter. So if you take a primary alcohol, right, so that carbon with the OH has 1 carbon attached to it, so it's primary. So if we react that with a reagent called PCC, so PCC is just a abbreviation for pyridinium chlorochromate, which is this. So if you take a primary alcohol and react it with PCC, so we're not going to get into the mechanism, so a lot of these mechanisms are fairly complex. Predicting the product is easy. Just take off hydrogen and hydrogen from the CO bond and you make a CO double bond, and that's your product. So now you have an aldehyde. So this reagent, so these chromium-based reagents are not very favorable to use because chromium, so this chromium's in the +6 oxidation state. So chromium is very toxic. So it's a very efficient reaction in organic chemistry, but it does have a downside because you have chromium salts that are very toxic, so you have to have very stringent controls on the how you handle the waste from those reactions. So another reagent that'll do that, what's called PDC, so that's just stands for pyridinium dichromate. So it's this is the reagent itself. So you should know the reagent and you should just know the name. So you may see either written on the arrow in a reaction. So a primary alcohol with PDC, same thing, just remove hydrogen and hydrogen from the CO bond and you make an aldehyde. So again, since the chromium salts are very toxic, there are better ways to do these oxidations now. So you can do what's called a Swerin oxidation. And it's a bit exotic, so this is your recipe. So you use DMSO. This is what DMSO looks like. You'll use this chemical, which is called oxalochloride, and triethylamine, and dichloromethane, typical solvent. So this is just a very mild way and a very efficient way to take a primary alcohol to an aldehyde. So the side products in this reaction, so you make dimethyl sulfide, which is a gas, CO2, which is a gas, carbon monoxide, which is a gas, and 2 molecules of HCl. So it's a very thermodynamically favored reaction because you make, 1, 2, 3, 4, 5 gases in this reaction, so it's a highly favorable reaction. So anyway, you should just learn to recognize, I'll say maybe I write on the arrow Swerin oxidation, or maybe I write on the arrow all of these reagents, and you should just recognize that's a Swerin oxidation, and it's going to make a primary alcohol into an aldehyde. Or you may see this reagent DMP, so Martin periodinane. So this is its structure. It's a fairly exotic molecule. So it's just going to oxidize a primary alcohol to an aldehyde. So we're not going to get into the mechanism, but one thing to recognize, so the carbon's being oxidized. So if something's being oxidized, then something has to be reduced. So what is being reduced? Well, it's the DMP reagent, and specifically the iodine is being reduced in the process. So that's your oxidizing agent. So DMP is reduced, and the alcohol is oxidized. Okay, so again, it's important to note if you have a primary alcohol what the oxidizing agent is, because if it's something like KMNO4 or H2CrO4, or the other one we saw was K2Cr2O7 and H2SO4. So these are all very strong oxidizing agents. And what they're going to do, so they would initially oxidize the primary alcohol to the aldehyde, but aldehydes are susceptible to oxidation. So once the aldehyde is formed, it can oxidize again and make the carboxylic acid. So with any of these strong oxidizing agents, primary alcohols go all the way to carboxylic acids, but with one of these weaker oxidizing agents or milder oxidizing agents, it'll stop at the aldehyde. Right, so that's what you want to note, particularly for primary alcohols, whether you have a weak or a strong oxidizing agent, because that's going to determine the product that you get out, whether it's an aldehyde or a carboxylic acid. So for a secondary alcohol, it doesn't matter. It doesn't matter what those oxidizing agents are, because they're all just going to do the same thing. They're going to remove hydrogen and hydrogen from across the CO bond and make a ketone. So it doesn't matter if you use one of the strong oxidizing agents or one of the mild oxidizing agents. They just remove hydrogen and hydrogen, make a C double bond O, and you get a ketone. And you don't have to worry about the over-oxidation. So another oxidizing agent that you can use is sodium hypochlorite. So just household bleach will do the job. So if you take a ketone with bleach and acetic acid as the solvent, then you'll make the ketone. And so here I do go through the mechanism. How does this reaction work? Okay, so hypochlorite will just pick up a hydrogen from the acetic acid. So acetic acid's an acid, so it's going to protonate the hypochlorite, and you make HOCl. And then that's going to react again to pick up another proton from the acetic acid. So you make this, and then that's what's going to react with your alcohol. So then your alcohol will react with the chlorine and kick off a water molecule. And then water molecule can take off a hydrogen from the carbon, and the CH electrons can become a C double bond O, and you lose Cl minus. And so that's where the oxidation is occurring at, right? Because you're making a CO single bond into a CO double bond. And then the last step, the Cl minus that you just lost, can take the hydrogen from the C double bond O, and now you have the ketone. So that's the basic mechanism. Okay, so if it's a primary alcohol and hypochlorite, then that's a pretty strong oxidizing agent, so it will oxidize it all the way to a carboxylic acid. All right, so take that carbon and make it into a carboxylic acid. Okay, so if it's HiO4, periodic acid, and you have a 1,2-diol, or vicinal diol, then this will oxidize it. And so what's going to happen here is you're going to cleave the carbon-carbon bond, and then you're going to make a CO double bond here and a CO double bond here. And so you're going to lose hydrogen, you're going to lose hydrogen from oxygen and make a C double bond O, but that hydrogen's not going anywhere. right? So if you did that, then this would be your product. So in this case, since both of these carbons had a hydrogen on them, then you'll oxidize to 2 aldehydes. But in this case, since that carbon has 2 carbons attached to it and this carbon has a hydrogen attached to it, so again, you're just going to cleave the bond between the 2 hydroxy groups, or between the 2 alcohols, and then you're going to make C double bond O here and C double bond O there, and then that's your product. So you would make that. So in this case, that's going to become a ketone, and this will become an aldehyde. And then this will be maybe more commonly wrote like 1, 2, 3, that, which is the same molecule, right? Okay, so inorganic esters. So we looked at reactions of alcohols and sulfuric acid before. So not from this particular alcohol, but if you had primary alcohols, they could make ethers, right? Or secondary alcohols or tertiary alcohols could make alkenes through dehydration reactions. But another reaction that could occur between an alcohol and sulfuric acid is similar to a Fischer esterification. You can lose a molecule of water. And since sulfuric acid has 2 OHs, right, you could do this to both sides, and then you can make what's called an inorganic ester. You know, so why is this an inorganic ester? So what is an ester? It's a C double bond O attached to an OR group, and you have something similar here, right? And you just have an S double bond O attached to an OR group, so that would be an inorganic ester. So this one's not particularly that interesting, but if it was nitric acid instead, you can make some interesting inorganic esters. So similar concept with nitric acid, you can lose an H and an OH, and you can make the inorganic ester. And this would be a particularly interesting one if this is your alcohol instead, glycerin, and you had 3 of these nitric acids, then you could make the nitric acids at all 3 OH positions. So you would make this molecule, which is called nitroglycerin. So that has a lot of uses. It has medical uses. It can be used to treat angina, but it also can be used as an explosive. So that's what you can use to make dynamite from. Or if it's phosphoric acid, then you can make some very interesting and useful inorganic esters here as well. So if it's phosphoric acid, since you have 3 OHs on phosphorus, you could make you could make a molecule like this. So again, there would be your inorganic ester. So that's not a particularly interesting phosphate ester, but this one is. So if you have this sugar, so this alcohol, where you have an alcohol there and an alcohol there, and if that reacts with so this would be H2PO4 minus, then you can make inorganic esters here as well. Right, so we could lose OH and H here and make a bond from oxygen to phosphorus, and we could lose OH and H here and make a bond from this oxygen to phosphorus. So that would give you a molecule like this, right, where you've made that oxygen-phosphorus bond and you've made that oxygen-phosphorus bond, and so this is what's known as a phosphate ester. A phosphate ester linkage, which you find that in DNA. So obviously this inorganic ester has a huge impact in biological chemistry. Okay, so lastly here, so we didn't talk about tertiary alcohols. So what if it's a tertiary alcohol and you'll try to oxidize that with one of your oxidizing agents? Well, this one you get no reaction. right? So you can oxidize tertiary alcohols without destroying the carbon structure, right? Because you can't make this, right? You can't make that C double bond O. Right, so what's wrong with that? Well, that would have 5 bonds on carbon. And you can't do that, right? So there is no hydrogen on this carbon. So you can't oxidize the tertiary alcohol unless you totally destroy the carbon structure or convert the carbon structure into something else. Okay, we'll stop there.